simpler. Alright, so it was much more simpler. So now let's see the code. Okay. Now, do take a look at your Google Classroom. I have added additional resources for you guys to go through. Alright, so let's take a look at the code. Alright, so this is the first method. Alright, first method on how to multiply two numbers. Okay? So you'll have the input of the first operand and second operand. Then we go through the loop. We find the summation. Okay? Now for the second type, okay? Now here, alright, so here, take a look at it. So we have one loop, okay, to read the positions, digit position, that means is it position 1, is it position 10, is it position 100, okay, alright, and then we have another loop to do the summation. Alright. Now by looking at these two algorithms, you just look at the lines. Okay? Now the first algorithm, do you think it's efficient? Is the second algorithm is efficient? How to know? Alright? So I think it's, there's just a few lines. So maybe the first algorithm is efficient. Alright? Actually, second algorithm is very complex. Alright? Maybe my second algorithm is, it's not that efficient. Or maybe my second algorithm is efficient. Alright? Yeah? So how are we going to find out the efficiency of this course? Okay? So that's what we're going to go through today. Okay? Alright, so basically even the simplest program, alright, can be significantly very inefficient. Alright, significantly can be inefficient. Alright, so of course the program which is insufficient, alright, will affect the overall performance, response time, which of course will translate to user satisfaction. If the system is slow, of course, as you guys, alright, have noticed, or you guys grew up with a very fast system compared to us, okay, my generation, very slow system. On the computer, alright, we can go and have a tea and come back, alright, and the internet, alright, those days are dial-up, alright, we have to literally call to the internet, okay, and then it takes such a long time for us to connect to the internet. But nowadays, how fast? Do you notice if your internet lags, do you get upset? Yeah, correct enough. Okay, so customer satisfaction is important here. So this is why we have to measure. We have to learn to measure the efficiency of our algorithm. Okay. So let's take a look at how we can measure and compare various approaches. Okay, the efficiency of the various approaches. Okay, now there are two main efficiency measurements, or how we can measure the algorithm: experimental study and analyzing the algorithm, analysis of algorithm. Okay. Now, when you say experimental study, okay, you're not looking at the content first. What do you think it will reflect? What do you think it reflects? What do you understand? experimental. What do you think it is? Alright? Experimental, what do?
You record the time.
Yeah? You do something, right? Okay? Yeah, you have to take the product to see the efficiency, and then of course you measure something. Alright? Now, analysis is what? So analysis is something like you need to calculate, you feel like you need to calculate, correct? Alright, you have to find something, alright? Okay, so now let's take a look at experimental. As our friend here say, experimental, alright? You have to measure the time, okay? So first, you implement your algorithm, okay? You finish your algorithm, you finish your program, okay? And then what do? You run the program on various input, whatever input you want to use. You record the time, alright? Record the time spent during each execution. Alright? This is the experiment. Okay? So we're going to correct, or we're going to collecting running time. We can use the system.current time milli. Alright? So here we record the execution. Before execution, we record the time, and immediately after the time. Okay, after we finish executing the algorithm. So we find out the differences and see how long it takes in order to execute, or how long it takes to execute the particular program or algorithm. Now, so which one will be faster? Algorithm 1 or algorithm 2? Alright? Until we code it and we run it, we're not able to find out. Okay? Yes? Okay. So now, so to have the code, okay, to go through the code, you must have the start time and end time. You figure out the differences. Okay? So for this, okay. Alright, so here the coding, alright. Okay, the coding, here we're going to put the value second operand, bigger value anyhow. Alright, so we check the start time, we check the end time, and figure out the differences. Okay, so by looking at this too, alright, then we'll be able to see which algorithm is faster. Alright, and in fact both algorithms are pretty fast. Okay, both algorithm is pretty fast. Okay, now because it's a millisecond, right? So we have to use nanosecond to actually find out the answers. Okay, which one is better? So there is another code for nanosecond. So this is for nanosecond. You can check on this, run it during your practical class, yeah? Right? So that is for capturing the running time. Okay? Now, what we have to do here in the running time here, if you are interested in general dependency of running time of the size and structure of the input. Okay? So we need to carry out independent experiment on a different type of data or input of various size. Okay, so you must run it for 10, you must run it for 20 data or input, you must run it for 100 data, and you must see the difference in time. Okay, so of course in order to find out different input set, you need to come up with some kind of visualization. Alright, will provide the execution time and the problem size. Now, do you understand when I say problem size? Problem size means I have 10 data to execute. 10 is the problem size. Okay, if I have 20 data, then 20 is the problem size. Okay, If I have 1000 and 1000 is the problem size, okay? Alright, so of course we need to provide some visualization, and this also involves in statistical analysis, okay? So to be very meaningful, we must have a very good sample input and have tested enough to make a sound statistical claim. Alright, so which one is the best? Okay, which one is the best algorithm or efficient algorithm? Alright, now, so that's the experimental analysis. Now, problem. What are the challenges we have? Okay, now running time. We are measuring running time. Alright, now what kind of computer you have? Is it i5, Core, which one? Alright, let's take a look at Apple, for example. Is it M1 or M2? Supposedly M2 is the best one, isn't it? Alright, do you think we're able to process faster? Okay, what if I have a supercomputer? Do you think I'm able to process much more faster? Right? Okay, well, if you want to check the efficiency, alright, if you are using same hardware and software environment, is fine. Your user going to be using a very low-end computers. So how efficient is your code when you are using like a supercomputer to test it? Right? So that is the challenge, right? And another thing is that you will have a limited input set. Alright? Wow, you are running your program. Wow, very fast scan. Oh, everything is okay. Alright? Then of course the user will use daily real-time data coming in. Alright? Then suddenly your system is not efficient. Alright? So for example, chat, for example, so you just tested with your group. Wow, chat working okay, fine. Right? Now we put our system live. Okay? The entire Thai UC students is using. So what we have about 10,000 people. Alright? Suddenly your system cannot work. Hang. Crash. Alright, so you see now that's another problem. Okay? Alright, and finally, alright, the challenges with your experimental analysis is you need to fully implement it. That means you must develop the program. Okay? And then it's not efficient. What happened? Have to go back to the design board, isn't it? Alright, that's going to take a lot of time and effort, right? Yeah? So this side, we have another way to measure our algorithm. Okay, we use our analysis of algorithm, the second method. Okay? This is the process of measuring the complexity of an algorithm. Alright? We use space complexity and time complexity. Alright? What is this space? Alright? Whether the memory required to execute this code is efficient. Okay? Time. Whether the time the code takes to execute. Alright? Now, for example, alright, phones nowadays, we have the memory, right? Okay, which one is better? So now, 250 what? Giga.
36.
256 gig. Memory enough?
Memory 256 gig in the phone?
That's what I'm asking. Is it 250?
That's too much already.
Too much already. It cannot handle. Alright? So what do you have on our phone? Right? What is your memory? Okay? But compared to your laptop, what is your memory? Alright? What is your memory? So phone is faster. Alright? Or your laptop is faster.
My laptop is faster.
Of course, laptop is faster, right? Right? Do you understand now? Okay, so now you want your application to run on the phone, right? So what do you have to do? Right? So you have to compensate, isn't it? The speed of the memory. So it's the resources, not necessarily memory, but it's more of a resources that you're going to use. Okay? So take a look at these two types. So one is the space and one is the time. Now, try to understand here. Okay? We're going to concentrate on time. We're going to concentrate on time complexity. Okay? Alright. Now let's move on. Moving along now. Due to the shortcoming of experimental analysis, okay, so for experimental analysis, alright, remember hardware, software, yeah, hardware, software, what's wrong with the hardware, software, okay, hardware, software, because for experimental study, the developer side can use high spec, high capacity machine. Alright, for the user side, they can have a normal low range computer, so that will be a problem. Okay? But for the analysis algorithm analysis, okay, is independent of hardware and software. Irrelevant what hardware you use, what software you use, we are able to measure the efficiency. Again, same thing. You don't need to implement the entire system like your experimental analysis, okay? And then of course you will take in all the possible input. Alright? So this is basically the goal, right? Alright, so we're going to concentrate on time complexity, alright? So we're going to pay attention the actual time needed for algorithm, okay? To compute, right? Alright, now the actual time needed for algorithm is difficult to compute accurately, therefore we do estimation. Alright, best, average, and worst. Okay? So let me give you an example. Alright, do you know dictionary?
Yes.
Alright, dictionary. How a dictionary is organized?
Alphabetically.
Alphabetically. Can you find what is the N? A-N. Meaning? Can? Alright? How many pages would you think you will flip through? Few pages? 1 or 2 pages? Few pages long. Alright? Right? 1, 2, 3, A. Then you go to A-N. Right? Yes? Okay, if I ask you to find out what is zipper, okay, imagine you cannot go to the last page, you have to flip all the pages. Alright, I want you guys to find out the meaning of zipper. What do you think? How many times pages you going to flip? So let's say your dictionary is thick. Many times? Many times? Right enough. How long it will take for you to flip? 5 minutes? Say 5 minutes. But the first word, let's say even it's apple, how long it's going to take? Maybe 30 seconds? Flipping? Yeah? You see? Apple, to find apple is the best case. To find the zipper is the worst case because it's all the way to the end and we have to flip all the pages. Do you understand? Alright, so that is best case, average case, and worst case. Okay, so we express time efficiency as factor of problem size when searching a collection of data. The problem size is the number of items in the collection, right? Okay, now I'm going to give you a little bit of example. Just now I said dictionary, okay? Now I'm going to use another method. Okay. Say I have a jar. Okay. I have a jar. Okay. Inside a jar got peanuts. Okay. Say I have a lot of peanuts. Then I have a small jar, and inside it also got a lot of peanuts. Okay? Now, which jar will take a longer time to count? Jar A or B? Which jar? Which jar will take a longer time to count the peanuts? Hey, come on. A or B? Sibling. Yes? A or B? A. Alright. Why do you think A? Because the input size is bigger. Alright? The problem size is bigger. Alright? So that's what it means by, alright, the problem size is the number of items in the collection. Alright? Now, another thing I want to say. Okay? Now, what if I tell you, okay, what if I tell you this jar contains this much of peanuts and this jar contains this much peanuts, or this much or this many, okay? Alright, what do you think? Which one you will take longer time to count? Alright, what is the box or a jar A? How many peanuts is in jar A? Hey, come on, are you counting? Are you looking? What are you doing? Jar A got how many peanuts? Yeah? How many peanuts? 100. Did you count? Did you take longer time? How about jar B? This is known as constant. Okay, remember this word, huh? Okay, constant. Is there any time required to count? No, you already know the answer. It's already listed there. So this is known as the constant. Okay? Earlier, alright? Earlier, we don't know the numbers. We have to count one by one. Okay? Bigger the problem, more time we're gonna take. Okay? So you understand all this here? Okay? Another example would be, alright? If you have to look a word in a dictionary. So now let's imagine you can just flip where you want the dictionary. If I ask you to go and find out what is match means. Okay, match means. So what are you going to do? You're going to start from A. In this case, we can just go straight. You're going to start from A. No, right? You're going to start from M. Correct? So how for the dictionary, okay, you can cut off. Okay, you start from R. Okay, understand this. Remember, later we'll come back to this. Okay, yes? Alright? Okay. Now you have a storybook. In the storybook, I ask you to check for a particular word. Let's say I want to check structure. The word structure in a storybook. Alright, where do you start? Where do you start? The storybook, this word, the structure. Where do you start? Compared to dictionary. Dictionary, you know, you have to start from S. Okay? But in storybook, you don't know where is it. The alphabets are not arranged according to alphabetical order. Right? The words, okay? So of course you have to start from page 1. So which one will take longer time? The dictionary or the storybook? Longer time. The storybook, right? Yes? Okay, so remember how you organize your data. Alright? In dictionary, I know I already organized the data from A to Z. In storybook, there's no organization at all. Okay? We just have words there. Alright? So in order to search for it, we have to start from page 1, word 1, line 1, and so on. Okay? Alright. So now back to this. Okay? If you want to find out what is the best case, average case, and worst case, okay? We are using time efficiency. Now, how are you going to calculate that? Okay? So, in order to analyze the running time, alright, without performing the experiment, we analyze the algorithm by counting primitive operations. Okay? Now, for job A, how did you find out the number of peanuts in the jar? We have to count. Correct? So similarly, how are we going to find out efficiency of growth? We have to count. What we have to count is primitive operation. What is primitive operation? Assigning value to a variable. Assigning value to variable is what? A equal to 10. Job A equal to 10. So we have to calculate this. You understand? Then we have reference, arithmetic operation. Arithmetic means add, minus, multiply, and divide. Comparing two numbers. This is the logical expression. Alright? Array, call method, and also the return method. Okay? Alright, so instead of trying to determine a specific execution time of each primitive operation, we simply count how many primitive operation executed and using this number T timer to measure the running time. Okay? Now, what we're going to do is that we're going to measure the algorithm performance, okay, using the number of primitive operation available in the code because it's proportional to the actual running time. Okay? So now we're going to measure in terms of function of input size to capture order of growth. Okay? Order of growth. What do you understand by the word order of growth? Growth is what? Growth. Alright? 10 years old? Are you guys like this? Yeah? Small, tiny colors. Now you're already tall. Yeah? Growth. Size. Increase. Okay? So order of growth when input size, alright, increases. Okay? When the input size increases, your time, computational time also will increase. Okay? Earlier, I said, small jar will take, let's say, 5 minutes to count. Bigger jar, more input, it will take, let's say, 20 minutes to count. Do you understand? Alright? Understand the order of growth. Okay? Now, to capture the order of growth of an algorithm's running time, we will associate a function called fn. Alright, this function, this is the input size. Okay? N is the input size. Okay? Alright, so now average. Remember just now I talked about finding the word apple and then finding the word zipper. Okay? Now we know few pages here, but all the pages for zipper. Okay? Sometimes it's quite difficult to figure out the average. Okay? To figure out average. So what do you do is that, okay? Algorithm may run fast on some input, then it does on other input size. Thus, we may wish to extract the running time and algorithm as a function of input size. Okay? Now, to obtain the average, We must take the average of all possible inputs of the same size. Unfortunately, average case analysis is quite challenging, okay? Because we have to use the probability distribution. Okay, so that's why we focus only, or we focus more on the worst case scenario. Okay, worst case scenario. How long does it take to count the bigger jar number 8 just now? Okay, we only worry about that. Smaller jar, I know I will take a faster time to count. Okay, worst case analysis is much easier than average case analysis as it requires the ability to identify worst case input, which is often simple. Okay, so let's take a look at this. Alright, now, why do we have to worry about worst case scenario? Okay, if I were to tell you, alright, if I were to tell you the exam is going to be difficult, okay, what is the worst case scenario?
Difficult.
You're going to be failing the paper, right?
Yeah.
That is the worst case. What else can be? Alright? Worst case scenarios, you're going to fail the paper. Alright? That's what we don't want to happen. Is that correct?
Yes.
That's what we don't want to happen. So what do?
Study.
Alright? Because we want to prevent the worst case problem, worst case. What we do? We try to prevent it. How you prevent in this case? Of course, what are you gonna do?
Study.
You're gonna be nice to me so I can give you more tips. Right? Of course, you're gonna study, right? You understand or not? Alright? So, that's why it's important for us to focus on the worst case. If in the event our efficiencies have a very long time to process a certain data, and that's where we have to worry about. Okay? So now, this is the formula. Now, I think some of you already know, okay? If I have a number, I want to plus like this, okay? Until 10. What is the value? Anybody can tell me? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Okay? How you do? You can use the formula. Okay? This is what we call induction proof of formula. Okay? Alright, what is this? How I can use this formula? How can I use this formula? So let's say I want to count until 10, right? Okay, I want to count until 10. So my n value is 10. So can you do the formula for me? And tell me what is the answer? Sorry, this is 10.
这个很像 arithmetic formula.
So here 11 times 10. So what do you got? Divide 2. So what's the answer here? What's the answer? Can you check? Anyone? So this is the 110 divide 2. Is it correct? How much? 50. 55? 55? Alright. So similarly, if I were to increase the n value to 1000, do you think you can do it quickly? Yes? Yes, isn't it?
Yeah.
Right? Now, okay, remember 1 plus 2 plus 3. If you were to do like that, it's going to take longer, right? Yeah, it's going to take longer time, correct? Alright? But if we apply a formula to it, it's going to be much more faster. Okay? The reality is, we do the normal way, it's going to take a longer time. But when we apply formula, maybe we can shorten the time. Okay, you understand? So we have to look at the worst case and come up with something to make it better. Even though the what do you call this, the input size can increase, right? But it is still able to salvage it. Okay. Alright, so now let's apply all we learned. Okay, apply how to measure. Okay, there's 3 algorithms. Okay, what we do with these 3 algorithms? So just now what I told you, 1 plus 2 plus 3 plus 4, right? There's a formula for it, right? Remember? Okay, we have 3 ways to execute that particular problem. Okay, solve the problem. Okay, there's one algorithm A, B, and C. Alright, the last algorithm, just simply apply the formula in. Right? The first algorithm, you have sum equal to 0. Okay, and then we have the loop. Okay, we're going to go through the number n value. So let's say 1 to 10 means n will be 10. Alright, so you're basically doing this in a loop. 1 plus 2 is how much? You put it into the sum 3, and then of course plus 3. Okay, this is how it's going to go. Yeah, correct? Okay, we are doing the same thing. Output is the same. Alright? Remember, I think during one of the practical class I said, yeah, your output is correct, but the way you are doing it, efficiency is important. Okay? Now, let's see B. What do you see in B? Okay, what do you see in the B? We have 2 loops. One loop is going through 1 to the input sign. The next loop is going through 1 to I. So this is the I. Okay? So when I is 1, so you sum up 1 to 1. Okay? And when I is 2, so you sum up from 1 to 2. Okay? This is how it's going to go through. And finally, of course, we have the simple what do you call formula. Okay? Yeah, got it? You see the difference here? Okay, let's see. We need to analyze our algorithm. We need to analyze. How do we analyze our algorithm? We have to calculate the primitive operation. Okay, what are the primitive operations? Assigning a value to a variable. Okay, let's see. Assigning a value, assignment. Okay, assigning a variable. Okay, so when we assign a variable here, can you see this? Alright, so how we assign a variable? Where the assignment is? It's drinking here, you guys. Oh, say. How can you drink without sharing with me? Huh? I tell you, I'm not going to share any tips with you. Alright, assignment. Okay? Assigning a value to a variable. Assigning, I got one assignment here. Okay? You understand? Now, here also the assignment. Okay? Assigning I value. Okay? How many times am I assigning? One time here I am assigning. Okay? Do you understand that? Assigning a value. Sum equal to 0. One time only I do. I equal to 1. I equal to 2. I equal to 3. How many times? N time. Correct or not? N is the number, the input, right? So if I want to add right up to 5, N will be 5. Right up to 1000, N will be 1000. Okay? N. N can be any value. Alright? Now here, okay, assignment, I have n and 1. Yeah? Correct? Okay. Now we see addition. We see addition. Okay? How many times this addition is, we have sum plus I. All the time sum plus I. Okay? We have one addition. So this is how we count. Okay? This is how we count. So we got one addition. Okay? Similarly here we count. Okay? We have one assignment, two assignment, three assignment, and we have the, okay? So we have this. And last one, okay? I will go through again. So we have one multiplication, one addition, we have one division, and one assignment. Okay? See that? So we put all one. Okay? So we total it up. Okay? We total this up. This is the value we are getting. We total all this up. This is the value we are getting. And this is the value we are getting. Okay? So let's take a look at it. How we do it. Alright? So algorithm A, total operation is total assignment plus total addition. Do you understand, Anna? Yeah? Assignment means you assign the value. Total addition, right? Okay? This is your total addition. So I already explained to you. Is there anything you don't understand? Okay? Anything you don't understand? Can So see this value here. So I just translate it here. So I add all this up and this is the value again. Okay? This is analysis. We are analyzing it. Okay? Alright? So how we analyzing it? We are counting the primitive operation. So similarly here, like when I is 1, your j will be 1 to 1. Okay? Total will be 1. When I is 2, j will be 1 to 2. Okay? So again, we calculate all this and this is the value we are getting. Alright? Okay? Now, you might find this, what is this now? Very intimidating. Okay? Now, simple. Alright? Simple, huh? Alright? When you have two loops and those two loops, okay? You see that we're using I here, alright? So this two loop is n multiplied n. This is 1 here, and this is n. Alright? This is number of times. How many times you're going to sum up? Okay? Now, can you see this? So I have n times n is n power 2, n squared 2 plus n. Now why I say this is n? Why I didn't say this is 1? Why I say this is n? Alright, because of the loop, yeah? So if the input signs increase, the summation also will be increased. Okay, how we sum up, how we total up. Okay? Alright, so always remember, alright, try to remember your loop is nested loop means it will be timed. Okay, so the rest will be added. Okay, so here that's the value given. Okay, next one. Alright, next one. Operation we have assigned total multiplication, division, addition and division. All we have 1 here. Remember I told you 1, 1 and here 1. So all these are 4. Understood enough? Yeah, okay. So now let's compare algorithm. Okay, this is how we're going to compare. What do you see? Which algorithm you think is the best by looking at it? By looking at this chart. We have n. N value is here. If n is 2, n is 1, n is 3, n is 4, n is 5. Algorithm 4, number of operations, stagnant. Alright, constant. Alright, what happened to algorithm B? Alright, the minute your n value goes up, alright, you see it's very low here, even lower than the operation for operation or what you call this algorithm C. It's low here. Then you increase your number of n value. What happened? Whew, it's going up. Correct? Okay. So you think algorithm B, if you increase the n value to 1000, do you think the time taken will increase? Can you predict? Yes, okay, time taken will increase because 5 is going upward already. Okay, and upward is not like algorithm A. Algorithm A is fine, still moving slowly only. Okay, so which algorithm would you use? By looking at this. When you increase your input, which is staying constant? C, isn't it? Right? Because we are using formulas. Yeah? Constant. Okay? Alright, so okay, I want you guys to take a break. I see our friend is nodding off, okay? So take a 5. Alright, yeah, all the lunch coming in too slowly. Alright, take a 5.